Welcome back. This is our Chapter 3 review on Freefall. We're reviewing for the test tomorrow, and this is number 3 of the practice problems that I gave you. So let's get started. All right, we've got a ball that's hit straight up and stays in the air for 5.6 seconds. So let's just draw kind of what's going on right here. I have, I'll draw it over here on the far left. Doesn't need to be real big. And the ball is hit upwards and comes back down right here. And the time, I'm going to call it time total. T-O-T for total is 5.6 seconds. Now I wrote time total for a reason, partly because I know how we're going to do this, but that simply means that that's going to be the total time that the ball is in the air, up and down. Well, so we're being asked here now how fast it was initially launched. So the VI, that's going to be what we're looking for right there. What else do we know? Well, we know our acceleration. Acceleration is negative 9.81 meters per second squared. And the question is, do we know anything else? And the answer is not explicitly, it's not being told to us outright. Usually when we try to find the initial velocity, it means we know the final velocity or vice versa. But we don't know the final velocity. We don't know this right here, which is our VI, or this right here, which is our, you might call it your V final. But we do know one velocity in this whole trip, and this is this right here. I'll call it my V max. That's the maximum height right there. And what is that? Well, we know that to be 0 meters per second. Up top right there. So why don't we take this whole trajectory of the ball and why don't we just cut it in half? Use my black dotted line right here. I'm going to dot a line straight up. Now this is one of the last things we talked about in our notes, but if we have a ball under, or anything under free fall the whole time, if we cut it right in half, that is if we split it right about the central axis or right around the maximum height, it's going to be symmetrical. So that means that the amount of time going up, call that T up, is the same thing as the amount of time coming down, T down. I'll write it real big, kind of like that. Why are we doing that? Well, because we can take half of this trajectory and we can call, since we know what the maximum height is right here, we can choose to either call that our initial velocity if we're looking at the second half, or we can call it our final velocity if we're looking at the first half. Let's just look at the first half because we want to know what the initial velocity is. So let's only look at this part right here and call our maximum velocity, our maximum height, or our Vmax, we'll call that our final velocity. Our Vf, what is that? Well, that equals our V maximum, and that equals 0 meters per second. So it's really just on the up side. Well, if that's the case, we need to change our time because time is for up and down. So let's just take our time and cut it in half. Let's say our T up is equal to half of 5.6. That should be 2.8 seconds. And now, since acceleration is the same for all time, we have an initial velocity, we have an acceleration, we have a final velocity that is for the first half, and we have time for the first half. All of that can be used to calculate the initial velocity, which is what we're trying to find. Initial velocity. So let's use our initial and final velocity equation. That is, final velocity equals initial velocity plus acceleration times time. Let's solve for initial. That is our initial. I'm just going to subtract AT from both sides. That's our final minus acceleration times time. So initial velocity equals, what's our V final? That's 0 meters per second minus negative 9.81 meters per second squared times t, which is t up is just 2 seconds, or 2.8 seconds, right? 2.8 seconds. So really, we're going to wind up with a positive answer right here because we've got a negative, we're subtracting a negative. So we're going to find here that our initial velocity, our VI, is going to be equal to 27.44 meters per second. 27.44 meters per second. Now the question is, how high did it go? How high did it go? So that's going to be our displacement. That's what we don't know. So we could say that that's our y final. Remember, the difference between our final displacement and our initial displacement is the change. But since we don't know the final or the initial, and we're just assuming that starting from the ground and going up to a maximum height, we'll just call that change. We'll just call it our change in y. We'll just call that our total change in displacement here. So that's what we don't know. What else do we know? Well, we know that assuming this is on Earth, gravity is negative 9.81 meters per second squared. And we know that the time, let's talk about just the first half, because all we care about is just one half of it, right? Because we care about the height, not coming back down, but just the height. So our time is going to be 2.8 seconds. That's going to be half of the total time. Now, do we know anything else? We know that the final velocity, VF, is 0 meters per second. Again, this is assuming just the first half, the ball starting and going up into the air right here. If this is our ground level right there. So it's our V final, it's 0. And we should know, well, we think we know the V initial, that is VI equals 27.44 meters per second. But I'm going to just kind of box that off right here, because again, since that's an answer that we calculated from a previous part, I'd like to do my best not to use that. And we'll use that only if we have to. So we're solving for our displacement, we have acceleration, we have time, and VF. That is, our V final is 0 meters per second. Well, we can also think of this as VI. Why don't we change our VF here to VI? Now, I'm not just doing this arbitrarily. You might say, Mr. Matz, well, how can you just change that to VI? Well, because let's just think of this now as in a different way. Here's the ball, or here's the ground, that is. And instead of thinking about the first half, let's think of the second half. The ball is starting up in the air and then coming back down to the ground. So that's our VI right there, and our VF is there. So even though this is the same velocity as right here, when we called this our VF and this our VI, it's the exact same thing. So let's just call that our VI. Let's think about the second half of the ball's trip up in the air and back down to the ground. And we can start at the top and call that VI. So VI is 0 meters per second. The time is still 2.8 because it's simply the second half of the ball's trip. The acceleration is the same, and the change in y is going to be the same as well. Actually, it'll be slightly different. The change in y right here, that is our displacement, is going to be the same amount. That is, in terms of how high did it go, it's going to be the same scalar value. But if we look at the second half here, we're going to find a negative displacement because the ball is going to be displacing downwards. But we'll just take the absolute value of the final answer that we get for y, and that's going to be how high it went, or how the highest it went off the ground. So let's find an equation that has change in displacement, acceleration, time, and initial velocity. So we're going to just ignore this for now because we don't want to have to use that. Well, we do have an equation that involves all those. We have our change in displacement equals initial velocity times time plus 1/2 times acceleration times time squared. So our displacement is going to be, what's our initial velocity? This is the second half of the ball's trip now. That's going to be 0 times time. That's going to equal to be 0. Plus 1/2 times acceleration, which is negative 9.81 meters per second squared. Times time squared, which is 2.8 seconds. That quantity squared. I guess I should have written it in here for t, but we know that's going to go away anyway, so I didn't bother to write it in. So that's going to just cancel out. And we're going to have our displacement is, I'll just do this in decimals, or the half in a decimal, 0.5 times negative 9.81 times 2.8 squared. What is that if we calculate that all out? It should be 38.4 meters. Actually, well, that's going to be negative, right? That's going to be negative, but since I said we'll take the absolute value, of y, because all we really care about is what the displacement is, how high it went. It's 38.4 meters. I guess you could also think of it as being, starting at the top, how low did it go? And that would be negative 38.4 meters, but that's simply just the change in the displacement, 38.4 meters. There's also another way to do that as well. I'm not going to go into it now, but it would involve using this answer from the previous problem. And I want to encourage you to avoid using previous problem answers if you possibly can. If you absolutely need to, then that's perfectly fine. Just make sure your previous answer is correct. Okay, that's 3A and B. Let's go on to part C.